All right, so we're going to prove that the quotient ring is a field. That's what the first statement here is saying. Every non-zero element having a multiplicative inverse will tell us, together with the fact that it's a commutative ring, tells us it's a field. That happens if and only if M is irreducible in K of T. Okay, that's the only time that happens. So if M is reducible, it's not a field. In fact, it's not even a domain, as we'll see. So suppose that M is reducible. So we're going to do the forward direct. Let me say it this way. We're going to do the forward direction by contrapositive, and then we're going to do the backwards direction directly. So for the forward direction, the contrapositive of the forward direction is suppose M is reducible. Then M is A times B, where the degree of A and the degree of B is less than the degree of M. All right, well, what must be true? And they're, of course, bigger than 0. Then A and B, I'll indicate what they look like in the quotient, are both non-zero. Because the only way that they could be 0 is if they were multiples of M, but they're not. They're a degree strictly less than M. Okay, so they're non-zero. And A bar times B bar is AB bar is M bar is 0. So we have 0 divisors. Which are non-units, which do not have multiplicative inverses. Ever. They never have multiplicative inverses. Because they go into 0, so you can't create one from it. So a quick proof is AC is 0, or AB is 0. This is just a general fact, so I'm just stating it as a general fact, but if you want to see a proof, you can look at any ring theory book, or AB is 0, and if CA is 1, then CAB is C0, which is 0, but it's also CAB, which is 1B, which is not 0 because B is non-zero. That's a contradiction. Okay, cool. We have 0 divisors, which do not have multiplicative inverses. Great. In the reverse direction, we're going to suppose M is irreducible. Then what? Well, take any A bar in K join T mod M, and which is non-zero. Okay, so A bar, we are going to abusively refer to A bar as its polynomial, the image of a polynomial here, and it's also its representation in the polynomial ring. So again, the degree of A is, well, it's bigger than or equal to 0, but it's also, because it's non-zero, and it's also less than the degree of M. Thus, what must be true? Well, the GCD, let me actually delineate the two real quick. It won't take too much time. Let's let A be any polynomial equivalent to A bar. So you could take just like the same coefficients and lift them up. I just want to take something that reduces to A bar. Then what? Well, the GCD of A and M is either 1 or M, as M is irreducible. If M equals the GCD of A and M, then M divides A, which implies that A bar is 0. If M goes into A, I must reduce to 0 because I'm a multiple of M. Thus, the GCD of A and M is 1. Let's let X and Y in K join T B Bezier coefficients. So that AX plus MY is 1. Aha, Bezier coefficients coming in, save the day. All right, AX plus MY is 1. All right, now let's reduce mod M. So we're going to get A bar, X bar. The MY goes away, equals 1. And so A bar has multiplicative inverse X bar. Nailed it. All right. So what did we prove? Well, we saw that if you're reducible, you get 0 divisors by your factorization. So your factorization gives you the 0 divisors in the quotient. If you're irreducible, you can find Bezier coefficients for non-zero elements, and the Bezier coefficients are they tell you what the multiplicative inverse is going to be. They give you a formula for it. And remember, just as an aside, not really relevant for this class, but as an aside, these are computable, right? There's an algorithm with the extended Euclidean algorithm. And that's an incredibly efficient algorithm. So these are very easy to compute. Anyways, you look at Bezier coefficients in the irreducible case, and that gives you the multiplicative inverse. Oops. And if you go back to the proof that Z mod P is a field for P prime, it's exactly the same thing. Or if you go back and you look at, like, in group theory in 5600, what the units are in Z mod M, the proof's exactly the same. You look at Bezier coefficients. So Bezier coefficients are incredibly helpful, as I said they would be, and they're helpful here. But nevertheless, what we need to remember here is that we get a field precisely when M is irreducible and only when M is irreducible.